right, so welcome everyone to What Physicists Do. This week, it is my pleasure to welcome Dr. Cora Fujiwara. So Cora was born in Southern California, like I know many of our students were. She then got her bachelor's degree in physics from Berkeley before heading down to Santa Barbara, where she attended UC Santa Barbara for her PhD. She's now a postdoctoral fellow at the University of Toronto, so up in Canada. So today she'll be telling us about her work studying ultra-cold atoms. So she'll tell us about how to get ultra-cold. So welcome, Cora Fujiwara.
Yeah, thank you very much for that very nice introduction. And so today I'm very excited to talk to you about some of the work that I've conducted over the past 10 years or so, as Alex mentioned, at UC Santa Barbara and as well at the University of Toronto, where I'm based now. And so the title of the talk is Get Ultra Cold, Using Light to Cool and Trap Atomic Gases for Quantum Simulation. So what do all those words mean? So roughly speaking, our plan will be as follows. So instead of, say, taking a very deep dive on a particular topic, we're going to take sort of a zoomed out perspective today on the field of ultra-cold atomic physics. And so I can't go into detail on one specific topic, but we'll try to I'll try to give you a very wholesome perspective on the field. So our plan is as follows. First, I'll go ahead and talk about how we can use light, namely lasers, to cool and trap gases of atoms with lasers. And we're going to be taking advantage, our working model for atoms will be this sort of atom. Then I'll talk about how we can take those atoms, continue to cool them down, and we'll create ultra-cold quantum degenerate matter. And what happens is at very cold temperature, atoms, instead of behaving sort of like billiard balls, their wave-like nature will sort of reveal themselves and will start to manifest sort of what's called many-body quantum behavior. And we'll talk about how that happens. Then finally, I'll talk about some experiments, how we can use these ultra-cold atoms to study synthetic materials made of light. And so as you can hopefully tell, the sort of unifying theme is going to be light and lasers and how we're going to use those to really generate some really exotic states of matter and study them. After I talk about that sort of science, I'll then conclude with a short sort of discussion about what does actually work in a cold atom lab, and I'll show some fun pictures and hopefully give you an idea of what it's like to be an atomic physicist. And so what I'm showing you here on the bottom two slides, or sorry, these bottom two pictures, on the left-hand side is an image of ultra-cold lithium, which is what's called the Bose-Einstein condensate, and we'll talk about that. And I'm showing you on here in the bottom right is an image of ultra-cold potassium in one of these lattices made of light. Each of these little tiny lights is a single atom, okay? So let's go ahead and get started. So for, we're gonna, being a overview, we're gonna start way back and just talk about what an atom is. So, the concept of an atom is very old, right? It dates back to the time of the Greeks, say this by this fellow named Democritus. And this is the idea that you could take matter and cut it down into smaller components until there's some sort of, smallest unit. Of course, this is not true. And it was until maybe about the last 100 years or so that it became understood that atoms are actually composed of subatomic particles, namely, say, protons, electrons, and neutrons. And this is very nicely demonstrated by this Rutherford scattering experiment. And with the advent of quantum mechanics, it became understood that the energies of the atoms are in fact quantized. And one way to understand sort of the energies of these atoms is by this sort of cartoon Bohr model, where we imagine, say, a positively charged nucleus with an electron orbiting around in sort of these circular orbits. And one important feature of this Bohr model is the fact that as electrons hop down or up from these different orbital radii, is they'll emit or absorb photons with corresponding energy. And it's this fact that we're going to utilize to be able to show how we can laser cool, which I think is going to be a lot of fun. So of course, there are many atoms that comprise our universe. Which ones am I talking about? So of course, this is the periodic table, and there's a ton of atoms. But for the purposes of this talk, we're really going to constrain ourselves to this group one, this first column. These are these alkali metals. And the reason for this is that these alkali metals have a single valence electron, which means that they're pretty easily understood through this sort of simple Bohr model that I'll be talking about today, where there's only one single electron orbiting around. Furthermore, I'm going to be focusing just on these three atoms, namely atomic lithium, potassium, and rubidium. And so just to get everyone on the same page, this is their alkali metals. So this is what sort of look like. They're sort of these shiny materials. They're actually sort of bubblegummy-like. If you touch them, they're very squishy. However, when I'm talking about atoms in this talk, I don't want you to be thinking about these three metals, or these specific forms. I'm going to be talking about dilute gases of atoms. And what we're going to do is we're going to take these sort of metals and heat them up, and they'll sort of vaporize, and we're going to be working with the atomic vapor, okay? Great. So if I'm going to be talking about laser cooling, let's just talk a little bit about how atoms and light interact. Well, we've already talked about one mechanism, which is this spontaneous emission, right? Which is where an electron can, say, jump down from a higher orbital state down to a lower one and emit in a photon, where the energy of that photon is related to the frequency. So the important feature that I want to focus on is this sort of two-level model, where these radiuses are going to be described by, say, two different energies, E2 and E1. And as this atom loses energy, it will then emit a photon of corresponding frequency, such that both energy and momentum are conserved, right? So if the atom is in some initial energy, after the photon is emitted, it will then have a lower final energy, which will be conserved with the energy of the photon. But of course, photons also have momentum, so then momentum will also be conserved. So if this atom was initially at rest, it then emits a photon, because of conservation of momentum, it'll receive a little kick. So this is a concept of spontaneous emission. We can also think about the converse, namely stimulated absorption. This is the case where, say, an atom is in sort of this lower state, E1. It will then absorb a photon. And again, by conservation of energy, the final energy of the atom will be equal to the initial energy of the atom plus the final one. And momentum will also be conserved. So suppose this atom was initially at rest. It's going to absorb a photon and it will receive a little kick because of conservation of momentum. And furthermore, I just want to focus on the fact that this happens when this energy of this photon is resonant with this transition here. That is to say that the energy of the photon is exactly equal to the energy between the two states here. And this will correspond to the situation where there's the most absorption. If I were to say change the energy of the incoming photon, I'll get less absorption. And if I change even further, eventually I won't get any absorption at all. Okay, so these are these two concepts of spontaneous emission and stimulated absorption. And it's these two facts which will allow us to laser cool. So how does that work? Okay, so let's consider a little thought experiment where we'll consider, say, an atom moving with some velocity v in this rightwards direction. And what I'm going to do is I'm going to apply some laser light that is counterpropagating. And as a reminder, this laser light will be comprised of photons with some momentum. And also, this laser light will be what's called red detuned. And just some technical jargon, and all that means is that the energy of these photons here, hopefully everyone can see my mouse, the energy of these photons here is less than that energy of the transition by amount delta here. So as we discussed, the atoms are going to, say, absorb some of the momentum and then re-emit them via spontaneous emission. And the catch here is that spontaneous emission happens in random directions, but the absorption in this particular case occurs only on one direction. So on average, as the atom absorbs the photons from my laser beam and re-emit them in random directions, this atom will experience a force proportional to the photon momentum that's incoming multiplied by the rate that this atom is scattering these photons. Furthermore, there's another trick, which is the fact that this atom is moving with some velocity v. So these photons that are coming in will be, in the reference frame of the atom, be Doppler shifted. So instead of perceiving the light with a detuning capital delta, it'll be decreased to this lowercase delta, which is related to the velocity of the atom. which is to say that as the atom moves, the frequency of the light will change. So if you plug this into some equations for atomic physics, you'll wind up with this expression for the force. So it's a complicated expression, but you can understand it relatively straightforwardly by seeing that this first term is just related to the momentum of the photon with a minus sign, right? Because the laser light is counterpropagating with the atomic motion. And it's related to the scattering rate here. And all that's really important here is that it's related to this factor I, which is the laser light intensity. So the bigger the intensity, the more force it will feel. So if you do some math, eventually you can arrive and show that this force is proportional to the velocity with the minus sign. So if you think about your mechanics courses, that's friction, right? So that means that this atom is going to be slowed down. So if the atom had particular energy, that energy will be reduced by applying this laser light. That's cooling. And this is our basic model, how we can understand how laser cooling works. So now what I'm considering, that was a simple one-dimensional case. Let's make a trap and also cool in all 3 dimensions. So to do that, I'll take that simple one-dimensional beam and I'll just multiply it by 6 times. So I'll have one beam coming in from this side, another from this side, and repeat that in the X, Y, and Z directions. And for technical reasons, I'm also going to apply this, I'm going to utilize this electromagnetic coil to apply a spatially varying magnetic field. That's the technical detail. And so you can do this in the lab, and we get the following. So what you're looking at here is an image of trapped atoms inside one of these vacuum chambers. And so this little bulb light here at the center are actually a gas of lithium atoms. And what you're seeing is each of these counter-propagating laser beams are hitting the atoms. The atoms are absorbing that light and then re-emitting it via spontaneous emission. And when they do that, your eye, well, in this case, a cell phone camera, is capturing that. And that's what you're seeing as this fluorescence here. So there's a little video here, which I'll play. Hopefully I turned down the volume. And so what you can see here is this glowing ball at the center of this chamber. And those are lithium atoms, as I mentioned before, that are absorbing these photons and then re-emitting them in random directions, which your eye is catching out. You can ignore this sort of lens flare over here. So just zooming out, this is a similar picture of that same apparatus. And so as I mentioned before, this all occurs inside a stainless steel vacuum chamber because we don't want any other molecules or atoms interacting with our gas of atoms that we want to address. And it turns out that this corresponds to about 3 billion atoms or so at their temperature of amount of millikelvin. And I should point out that this temperature is limited by this constant gamma, which I haven't talked about, which is basically, it's called transition line width, which is basically related to the uncertainty in the transition energy. Okay. So 1 millikelvin, that's pretty cold, right? So, space is like 2.7 Kelvin, right? But this is a relatively small number of atoms. It's 3 billion. You should compare this to Avogadro's number. All right, so 1 millikelvin, that's pretty cold. But how can we get even colder? Okay. And so it turns out that there's another mechanism by which we can understand laser cooling. So the first one I just mentioned is what's called near detuned resonant absorption, which is what we just discussed, right? And that's where an atom is going to absorb a photon such that the force that this atom experiences is going to equal to the photon momentum multiplied by the scattering rate, right? And again, we're going to average out over spontaneous emission. And as I mentioned before, this temperature is going to be limited by spontaneous emission. So it turns out that there's another mechanism by which atoms interact with light, and that's called a far detuned dipole force. So let me go ahead and explain how that works. So we're talking about applying laser light to some atoms, and you should remember that light is an electromagnetic wave, which means it has an electric field. So that means that as the laser beam is going to be passing through these atoms, it's applying an electric field to them, right? And these atoms, again, right, they're a positively charged nucleus and a negatively charged outer shell, which means that on an application of this electric field, the electrons and protons will feel a different force, which which in opposite directions, which will create what's called a dipole moment, where there's a relative displacement between the positively charged nucleus and the negatively charged outer shell. And if you recall from your coursework, this creates a potential energy, which is going to be equal to the electric field multiplied by the magnitude of this induced dipole moment. And this will be our basic model for this trapping mechanism. And it turns out this potential energy is given by this expression here. And again, there's some constants which are important, or which are technically important, but for the purposes of this talk, the only thing that really matters is the fact that this dipole potential depends upon the intensity of the laser beam, and it goes as 1 over the sine of the detuning. And I should point out that this mechanism for trapping really only becomes the dominant mechanism when this resonant absorption force is very low. That is to say, at very large tuning. Okay. Great. So we're going to use this physical mechanism to create a new kind of atom trap. And I'd also point out that one advantage of this trapping mechanism is that there's effectively no lower temperature bound. Cool. So how do I make a trap of this kind? Well, let's take that gas of atoms that I was showing you previously, that fluorescing ball of lithium, and we're going to shine on this very intense laser beam, which is this far red tuned laser beam, and there will be a dipole potential, which is given by this expression top right, as I've shown you before. So what I can do is if I make this term delta here, which is the tuning, negative, that is to say red tuned, it'll be an attractive potential. And so atoms will be preferentially attracted to regions of highest laser intensity in this case. And so we can do this in the lab. And so what I'm showing you now is actual data that we've taken in the lab, which corresponds to those trapped lithium atoms in this new kind of trap, which we call a dipole trap. And so what's happening here is there's 2 laser beams, and we use 2 for just to confine things a little bit stronger, where one laser beam is going along this sort of diagonal direction, and there's another laser beam going along the other diagonal direction. And at the intersection of the 2 is where the highest intensity happens, and that's where these atoms are trapped. And this image corresponds to around 12 million lithium atoms, and they're a temperature of 2 microkelvin, right? So that's 1,000 times colder than I was showing you a few slides ago. So this is great. And showing you sort of a picture of some atoms. And so this is actual scientific data. So I think I'll just take a moment now to talk about how we actually take data in the lab. So the way that that image was constructed is with light. And so we have this gas, these trapped atoms over here, which is this blue sort of circle. We then are going to shine laser light on them, right? Which is going to be resonant with some internal transition. And as we just discussed, the atoms will absorb that light and re-emit it. But looking along sort of this propagation direction of this laser beam, that means that the atoms are going to cast a shadow, and we can image that shadow onto a camera with the help of a few lenses, which I've sort of diagrammed out here for you. Okay, so in practice, what this means is take a picture with the atoms. So here's a picture on the camera where I've turned on the light and there are atoms. And what you can see here is that there's a little shadow at the center, which corresponds to the fact that the atoms are absorbing some of this light. I'll then take a reference picture where there's no atoms. I'll also take a dark picture for background subtraction. And I can recreate what's called the optical density, which is basically related to the ratio of sort of the magnitude of the shadow that these atoms cast along this camera sensor. And that allows me to extract what's called the optical density. And that's how that image that I showed you previously was created. So it turns out that this optical density, these pictures, what do they tell us? It turns out that it tells quite a wide variety of information. Well, first of all, the magnitude of that shadow tells us the number of atoms present. It's a picture, so it tells us the spatial distribution. And then momentarily I'll tell you that it can also help us measure the momentum and energy distribution of the atoms. and can also tell us the magnetic state of these atoms. So there's a whole bunch of information that can be extracted from these sorts of absorption images. Great. So let me just show you how that works with the following example. So here's that image that I showed you before, where we have those atoms that are trapped in this dipole trap. And what I'm going to do is I'm just going to turn off my laser beams. So as I turn off my laser beams, these atoms have some sort of finite temperature. If there's nothing confining them, they're just going to expand in free flight. And we call this time of flight. So here are the atoms after half a millisecond of time of flight. And I'll let them expand. So here's 2 milliseconds. And I'll let them expand some more, 3 milliseconds, and 6 milliseconds as an example. And so again, what's happening is that these atoms that were once trapped are now freely expanding. And so what I've done here is created basically a rudimentary movie. This is what a basic movie is, right? Just a series of still images sequentially in time. And so if I stitch these two things together, I can make a movie, right? And so again, what's happening here is that these atoms are trapped, then we're letting them go and they're expanding. And because they have sort of finite temperature, their expansion is related to how hot they are. And that's this basic movie. So I can sort of do some fitting and extract the temperature in the following way. So here on the x-axis is this flight time. And the y-axis is the basic size of the atoms. And as the atoms expand, I can fit this to some known function, and that lets me extract the number of atoms and the temperature. And this is where that 12 million and 2 microkelvin came from before. Great. So now I've sort of, hopefully everyone's on the same page about about how we take data, and also when I say temperature, how we measure that temperature. Great. So with that being said, let's get even colder. And we're going to utilize a technique called evaporative cooling. So the way that we can understand this is through the following analogy. And so I just want to ask everyone, how does your cup of coffee cool down? Or in this case, my tea. Well, there are a couple of ways. Well, you could touch the cup, right? So the heat is going to transfer from your hand to your cup. Sorry, from the cup to your hand. Or you could say you could transfer heat from the cup to the table, conductively. But the primary mechanism by which your coffee is probably going to cool itself is by evaporation, right? So you have some sort of steaming hot cup of coffee, and there's steam going out from it, and that's going to carry a lot of energy. And so what's happening, as I just mentioned, is that the steam has a lot of energy, and so it carries it away. And as it carries more and more energy away, that'll make your remaining cup of coffee colder and colder. This is known as evaporative cooling. So the same sort of thing will happen in an atomic system. And we can utilize this fact to cool down to very, very, very low temperatures. So let's finish this analogy. So again, as a reminder, we're considering atoms trapped in this dipole trap, right? Which is where we have this very intensely focused laser beam, and the atoms are attracted to the regions of highest intensity. And then here's an image that we were just looking at prior. So from an energy standpoint, I can think about it the following way, where this sort of black line indicates basically the potential energy of my laser beam, right? So the sort of height here, this depth, is basically the maximum potential energy of my dipole trap, which again is related to the intensity of the laser beam. And sort of the size of the trap, right, should correspond basically to the size of my laser beam here. And so I can imagine that atoms are going to populate this trap. So the less energetic ones are going to sort of occupy sort of the middle regions. And the more energetic ones are going to be towards the top of this trap. And in this sort of analogy, those most energetic ones, if they have energy larger than the trapping, than the potential energy by which I'm applying to them, they can escape and leave the trap. So this creates cooling because as the hottest atoms leave, they leave behind a colder and colder remaining sample. And I can further encourage cooling by simply decreasing the intensity in my laser beam by just turning down the knob in the power on my laser controller, say. So as I turn down the power in my laser, this decreases the intensity, which creates a weaker trap, which means that the more atoms, the most energetic atoms can leave. And once the most energetic atoms leave, that leaves behind a colder sample. And hopefully you can see how this is basically analogous to the evaporative cooling, say, out of your coffee cup. And so this technique of optical evaporation allows in the lab to cool down from those 2 microkelvin temperatures to much, much, much colder temperatures. And that allows us to make quantum degenerate matter. So what do I mean by this? Well, as I mentioned before, usually when you think about atoms, you can think about little tiny billiard balls floating throughout space. But as we cool them colder and colder, their wave nature becomes more apparent, where their wavelength is related to this thermal de Broglie wavelength here, lambda dB. And what's important here is this wavelength goes as 1 over the temperature. So as I get colder and colder, the wavelength, the quantum wavelength of my atoms becomes longer and longer. And as this quantum wavelength becomes longer and longer, eventually those wave function of all those different atoms are going to interfere with each other. In the case of what are called bosons, which is a sort of flavor of particle, they will constructively interfere, and you'll get what's called this matter wave overlap. And eventually, as they get colder and colder, all the atoms are going to constructively interfere with each other, and we'll get what's called a pure Bose condensate, which is this giant matter wave where all of the atoms are in the same quantum state. And we can see this in the lab. So here, I'm showing you data in the lab. Again, this is after some time of flight. So the size of the cloud is basically related to the momentum distribution. So these are sort of momentum space images. And as I go from the left side to the right side, I'm getting colder and colder. And what you can see here is the formation of this little tiny hard core at the center of the cloud. And this is this formation of this Bose-Einstein condensate where all of those atoms are in the same quantum state. And so this corresponds to around a few 100,000 atoms that are all in the same quantum state with each other. And so I can show you on this bottom left-hand side here, I'm showing you sort of an analysis of these data, where as I lower the temperature, I can look at the number of atoms, or sorry, the percentage of the atoms that are in this condensate, and it approaches unity as I get colder and colder with a characteristic temperature scale of around 420 nanokelvin. So this is how cold we're talking about now, which is only a few hundreds of nanokelvin. And that picture that I showed you on my title slide and also the table of contents slide corresponds to basically a 3-dimensional rendering of this exact image. And so now you hopefully understand how this data works. Great. So as I mentioned, this is lithium forming a Bose-Einstein condensate. But as I mentioned before, I also work with other atoms. So I just want to briefly point out that you can do the same thing with the other atoms that I mentioned earlier. So here's a Bose-Einstein condensate of rubidium, which is a composite boson, and for other flavor of particle in our universe, which are fermions, or one of the other flavors of particles are these fermions. And in this case, this forms a degenerate Fermi gas, in this case of potassium. Okay, so I just want to mention that we do this with other atoms. So of course, I've glossed over a lot of technical details. So if you were a student working in one of these labs, there's a plethora of other steps that you'd have to understand, and I'm not going to talk about any of these things, but I just want to point out that as the atoms start off being hot and eventually becoming very cold, the sort of underpinning theme here is that for hotter stages, we use near to tune light, right, which is going to be laser cooling using that radiation pressure force that we talked about. And as I get colder, we'll use far to tuned light, namely these optical dipole traps. And so hopefully now you understand sort of the basic framework of how these experiments work. Great. So just sort of wrap up this section so far, what I've told you so far is that you can use lasers to trap and cool gases of atoms. And we can also cool them down to very, very low temperatures. I'm talking like tens to hundreds of nanokelvin. And when we lower them down to these very cold temperatures, their quantum behavior manifests, and we can create what's called this quantum degenerate matter, where all these atoms are in the same, they form one large quantum many-body state. And one thing that I haven't discussed for you is that not only can we not only can we create these new states of matter, we can also control a variety of the microscopic and macroscopic properties. So I've already told you about how we can control the temperature by, say, lowering the trap depth and letting the atoms escape. But it turns out that we can also, say, control the interactions between these atoms. So if you just sort of sit back and think about it, what we've made is we've made this sort of many-body quantum state, and we control a variety of its parameters. So with all of this awesome control, how can we use it? And what is this thing good for? We've made this really exotic state of matter. How do we use it? And so this will bring me to my next topic, which is this concept of quantum simulation. Okay, so this is kind of a complicated concept, but it works in this following way. So, and it works on this analogy between the realm of atomic physics and condensed matter physics. So condensed matter physics is a study of material science. And in materials, right, real materials, we're considering electrons hopping around inside ionic lattices, right? And I'm going to tell you that there's an analogy between electrons hopping around in ionic lattices to cold atoms hopping around inside optical lattices, which will be lattices that are made of light. And the reason why you want to do this is that we're going to try to use atomic physics to help understand and solve some outstanding problems in condensed matter physics. And so condensed matter physics, as I mentioned, is a study of materials. There are a really wide variety of really important physical problems that we would like to solve in condensed matter physics. So for example, if you want to understand how high temperature superconductivity works, or you want to understand, say, topographical, some insulator physics. These are really important physical problems that we like to understand. But one of the issues is that these are quite complicated. They have, say, complicated interactions, and they also occur at relatively large energy densities, right? So, you can't just take a solid and easily look at each individual electron on an atom. You could do this with, say, an AFM, but that also has other sorts of issues. Moreover, in these sorts of complicated systems, the parameters are fixed, right? You can't necessarily change the electron Coulomb propulsion. And so what we're going to do in atomic physics is we're going to bring a complementary perspective on how to solve and understand these systems. And so this is what I mean by simulate. So instead of considering electrons in ionic lattices, we'll put cold atoms in lattices of light, and then we're going to turn down all of the properties of the material. Namely, we're going to work at much, much lower densities, right? So instead of having angstrom level scales of interparticle spacing, we'll consider sort of micron scales, right? Because that's sort of this length scale of light. And moreover, as I just talked to you about, in these cold atom systems, we can control them very finely. We can say control the interaction between two atoms, right? You can control the interaction between two electrons. And we can also tune, say, the lattice potential, right? You can't tune the energy attraction between protons and electrons, but we can certainly tune down the laser intensity with just a knob. And so this is this concept of quantum simulation. Great. So I've talked about these optical lattices. How do we make them? And we actually make them relatively straightforwardly based upon the physics that we've already discussed. So as a reminder, here is this dipole trap that we've been talking about so far, where we have this laser beam that's intensely focused, and the atoms are attracted to the regions of highest intensity. And what I'll simply do is just put a mirror on one end. Well, what does this do? Well, light, right, is an electromagnetic wave. And so if I take one wave, which is going one direction, and I add a mirror and retroreflect it, this will make a standing wave of electric field. And if I time average over this electric field that's oscillating because of the standing wave, I'll get a periodic tiling in intensity, which is indicated by this red line. And as I've just talked about with this dipole potential, the potential energy is related to the intensity. So by having a periodic tiling in intensity, I'll have a periodic tiling in potential energy. That's a lattice, right? And so what I'm trying to say here is that this analogy is that there's a similarity between electrons hopping around in ionic lattices and atoms hopping around in these potential energies given by this optical lattice. Great. So this is this concept of quantum simulation. And now I'm going to talk about a couple of experiments that utilize this concept. So first, I just want to briefly talk about how we can think about the energies of atoms inside this lattice. So as I already mentioned, there's this periodic potential energy. This is sort of in position space. It turns out that for many applications, it's more helpful to think about the energy of these atoms in momentum space. But over here on the right-hand side, and I'm glossing over lots of details, is a plot of the energy states of the atoms inside these lattices, and they form what are called block bands. That's just a technical jargon for the purposes of this talk. The point is that the available energies to the atoms are indicated by these colored lines here. So there's a first energy level, which is this blue, the second one, which is this red one, a third one, which is this yellow one, and a fourth one, which is this purple one, et cetera, et cetera. And so on the y-axis is the energy, and on the x-axis is what's called quasi-momentum, which for the purposes of this talk, you can think about is just the momentum. So that is to say that the energy of these atoms is a function of the momentum, which should make sense. Great. And so if I take that Bose-Einstein condensate and I slowly turn on the optical lattice potential, what we can think about is our Bose-Einstein condensate is going to populate, say, this lowest energy state at the center here with zero momentum, right? Because my BEC is not moving. And so with this, I can ask myself, what happens first, or how do I understand some basic transport phenomenon? So the question I want to ask is, what happens when we apply a constant force to particles in a lattice? And the answer is what are called block oscillations. And the way that this occurs is that we're going to consider our atoms, which are going to be initialized here at momentum 0, and we're going to apply a force to them. And for, semi-classically, you can think about, well, F equals dp dt. So there's going to be a change in momentum because of this constant force. And so you can imagine that my little wave packet here with some sort of, with zero quasi-momentum is going to increase. And normally, right, if I applied a constant force to a particle in free space, it will just accelerate, F equals ma, so it'll just accelerate. But what turns out in a lattice is that instead of just accelerating, there's going to be a quantum mechanical interaction between atoms and the lattice. And what happens is as the atoms accelerate, eventually they will scatter off of the lattice potential. And this is a quantum mechanical effect. And this creates this sort of characteristic sawtooth oscillations in momentum. The frequency of this is given by what's called the block frequency, which is related to the force that I'm applying, the lattice spacing, and Planck's constant. And so block oscillations, and what I'm showing you here is an image of these characteristic sawtooth oscillations in momentum space. So block oscillations have been understood in momentum space for quite a while now. But it turns out that not only are there oscillations in momentum space, but there are also complementary oscillations in position space. And this is because of the fact that as the atoms evolve in momentum, they're also going to move with some velocity related to their group velocity here. Now, these position space block oscillations have been traditionally challenging to measure because the length scales are very tiny, and in a real solid state material, because of defects in electron-electron scattering, because of complications in real materials, they're relatively challenging to measure in position space for actual solid state materials. But in atomic physics systems, I'll be able to tune the interactions to 0, so there's no interaction-induced decay. And I can also amplify the magnitude of these oscillations by working with low forces. And so we can do this in the lab, and we can see very nice position space block oscillations. I'm showing you here as a time slice. So each picture here corresponds to a different moment in time, and the y-axis corresponds to position. And these are oscillations of the atomic position in the optical lattice as I apply this constant force. We can then compare this experimental data to theory, and we see excellent agreement. And this was a nice shout out from the editors at PRL. So Adams put a block party. And so I like to imagine that block and Zener, for which these block oscillations are named, or block bands are named after, are having a little party with party hats. Great. So I should also mention, though, that we can also analyze these systems and quantitatively compare the amplitude and say the amplitude of these positions, these block oscillations, in comparison to, say, the force and also this tunneling rate J, which is related to there's a technical detail related to the lattice depth. Great. So just moving on. Not only can we measure these position space block oscillations, we can also measure the momentum of the momentum oscillations as well, using that time of flight technique that I mentioned previously. So again, we're just going to let the atoms oscillate in the lattice and let them expand, and then their free flight expansion will be related to their momentum, which allows us to extract simultaneously both the position oscillations and momentum oscillations of these atoms, and allows us to reconstruct an entire phase space time evolution of the system in both momentum and position space. So there's a lot going on in this plot, but let me just go ahead and briefly explain here. So the atoms initially start off at some position. So the color map corresponds to time. And the y-axis corresponds to momentum. And the atoms will move and oscillate in position space. And eventually, at some finite momentum, they'll scatter off the lattice, as I mentioned, and you see a discrete hop over here where they've scattered some lattice momentum. And they'll continue on their merry way. And this is more of a complete picture of what's happening with these with block oscillations. Great. So now I want to move on and talk about a different experiment or a different setup, which is so far I've been talking about measuring atoms' momentum. But it turns out, as I alluded to in the beginning of my talk, that you can actually see individual atoms inside these lattices. And so I'm not going to talk about this in great detail, but the basic idea is let's go ahead and, instead of considering a one-dimensional lattice, we're going to make it three-dimensional by adding additional laser beams. And what we're going to do is we're going to have these atoms inside this lattice here, which is indicated in this cartoon right around here. And we're going to shine resonant light on them. And as these atoms, again, they're going to absorb these photons and re-emit them. If I have a lens which is really close to them, which is this sort of blue thing here, I can capture the fluorescence of each of those individual atoms and then put that fluorescence onto a camera. And that allows me to see individual atoms inside a lattice. And that's what this picture is here, is that each of these atoms, or each of these bright spots, correspond to a single atom absorbing and then re-emitting this resonant imaging light that I'm applying. And in the interest of time, I'll quickly go over this. We can also do other sorts of transport measurements by applying periodic forces to the system, which allows us to sort of measure the oscillations positions of the cloud as I apply a force, which in sort of a Ohm's law limit allows me to measure the conductivity. So here I'm showing you is a displacement, which is these blue dots, of the center of mass of the cloud as I'm applying a periodic force to them. And that allows me to measure a conductivity both as a real part and an imaginary part, where the imaginary part represents the fact that the conductivity is phase shifted. And I can also study how a variety of these conductivity parameters depends on, lattice depth. So in conclusion, hopefully I've provided a whirlwind perspective about how light can be a powerful tool for trapping and cooling atomic gases. And hopefully I've also convinced you that cold atoms can provide a rich playground for understanding and creating quantum matter. And furthermore, once you've created this quantum matter, I've shown you a few experiments how you can use these atoms in optical lattices to realize a variety of novel transport phenomena. And so I just like to acknowledge my group, or for my PhD, was under the advisor of David Well at UC Santa Barbara. This is the lithium team. And today, I'm now at the University of Toronto, and this is the group on the microscope team. So with the remaining time that I have, I just want to provide a quick perspective on what does it look like, or what does an atomic physics lab look like? So this is the experimental apparatus at UC Santa Barbara. So there's a lot of stuff going on. So we like to think about these as very complicated tabletop experiments. So if you've never seen this before, this is an optical table. And this is this sort of stainless steel vacuum chamber. And there's all sorts of cables which correspond to currents for electromagnets. Also a lot of optical fibers which carry over the laser light. And you can see a bunch of mirrors and a lot of glowing lights which correspond to all the different colors of lasers that we're applying. And I should also point out that if you work in one of these labs, you can actually build these. So this is what that same room looked like about 7 years prior. And this is what sort of the construction looks like from, this is these stainless steel chambers, which you can actually assemble if you're in these sorts of labs. And there's also another table which corresponds to where all the lasers are stored. So nowadays I'm at the University of Toronto. So if you come visit the city, our labs are located around here. And sort of experiment looks very similar. So here's a giant optical table. So here, the sort of golden colored thing is the stainless steel vacuum chamber where the atoms are trapped and laser cooled. And as is similar, there's a ton of optics and mirrors. And so if you are a student working in these labs, you would have to learn how to, if I were to say, touch one of these knobs, you'd have to figure out how to fix the machine. So you have to do a lot of optics. Here's some other pictures of the apparatus from different angles. Again, the same story where there's lots of mirrors and lenses. These little blue things here are some of the cameras that we use to image. And again, in the center here, which is here and here, is the stainless steel chamber where these atoms are trapped. And finally, I mentioned how the theme here is a bunch of lasers. You also get to work with lasers. So this is what a laser looks like in the lab. So say you were a student and you were interested in working in this sort of field, what sort of skills and things would you learn? Well, there's a variety of sort of practical and theoretical skills. So on the practical side, you would need to learn how to learn some computer assisted design. You would work with ultra high vacuum systems. Of course, you would learn about lasers and optics and all sorts of electronics and coding. And on the physics side, sort of the fields that we deal with on an everyday basis would be, of course, quantum mechanics, many body physics, statistical mechanics, electromagnetism, learn about quantum optics, and of course, atomic physics. And so I think if you're a student, you're interested in this field, I think there's a really good balance of both hands-on and theoretical skills. And so with that, I think I'd like to conclude and thank you for your attention and open it up to any questions.
Thank you so much, Dr. Fujiwara, for that amazing, very interesting and awesome talk. And I'll clap for everyone since you can't see the audience really. So if anyone at this time has any questions, you can either raise your hand or you could type a question in the chat. If you'd like to just ask the question vocally, I think raising your hand is the best thing to do, and I can call on you. It looks like Hong Tao has a question, so if you'd like to go first.
Yeah, thank you. That's a very interesting topic. So I guess my first question is about how you actually introduce these atoms into the chamber without really having them move in all different directions, so you can localize these atoms.
That's a great question. Let me have a better picture for you. Right. So on the way that we do this is it's right, because we can't just, as you mentioned, we can't just take atoms and put them into the chamber because that would say break vacuum. So on the top right here is what I'm showing you in that same image that I was showing you previously. And on the bottom is basically just a CAD rendering. And so what we do is we separate the regions from where the solid sample is and the trapping position is. So that's represented here on this far left side, what we call an oven. So there's a cup of these atoms, and then we heat the cup up, and that creates a gas. And by physically separating this chamber, we're able to transport the gas atoms from a very high vapor pressure region to eventually toward the main chamber. So it's all one physical object. Because of the fact that we separate them physically, we're allowed to have very large pressure gradients between a very low pressure region where we actually do the trapping and cooling and sort of where the atoms are actually generated with high vapor pressure. Does that sort of answer your question?
Yeah, but I guess, I mean, what happened to the diffusion? How can you stop the diffusion from happening in a vacuum chamber when the pressure basically tells you that the vacuum has such high or low pressure, and the induced gas is going to have a pressure slightly larger than your base pressure. So how do you stop these atoms from diffusing into the wall of the chamber, for example?
I see. So in the laser beam trap, they're sufficiently so, I guess from a length scale perspective, the atoms are about maybe like 10 centimeters away from the stainless steel chamber, the walls of the stainless steel chamber. So at those sort of distances, the surface forces that the atoms would feel with the chamber are relatively low compared to the trapping potential of our lasers. However, it is true that for this quantum gas microscope that I mentioned, where we have to have the atoms very close to this window in order to measure them. If you get them too close, there will be surface physics where there will be a significant van der Waals force between the atoms that are trapped and the stainless steel chamber. So you do have to worry if you get them very close, but for most of the time, they're around like 10 centimeters away. So surface level physics don't really play a strong role in that regime.
Okay, thank you.
So it looks like next we have a question in the chat. I'm not sure if you could see this, Cora. I could read it though. So it says, so Bill asks, so you're measuring both the position spreading and the momentum. So is there any impact of the uncertainty principle? And then you can use, or is this statistics and you're not measuring both quantities of the same object? So.
Yes. So I was sort of pulling a fast one. Which is the fact that, yes, we're not breaking Heisenberg uncertainty here, that when I'm constructing this phase space evolution, I'm not doing a simultaneous measurement. I'm doing two measurements, one where I measure the position and one where I measure the momentum. And because I'm utilizing the fact that I'm measuring an ensemble property, and as the fact that with these sorts of experiments, because lasers are very reliable, I can create an identical ensemble every single time. And that allows me to create unique instances of an identical system.
Awesome, thank you. So are there any other questions from the audience?
Yeah, Alex, can I ask another question? I'm sorry, go ahead, whoever the person is.
I was gonna ask, how are you getting rid of the heat? You're adding energy, and especially during evaporative cooling.
Mm-hmm.
The electrons, I guess, are coming out of the energy trough, but that's temperature. Where is it going, or is there a kind of a temperature gradient down the length of your lab setup, and so colder goes to the right, and everything, and hotter, even though it's very cold, sort of stays and up further upstream?
I see. Yeah, so this is a great question. So what's great about these sort of atomic systems is that because all of these potential energies, or all of my trapping potentials, are made of light, and all these atoms are inside a stainless steel chamber or inside a vacuum chamber, they're extremely well isolated. So that allows me to maintain effectively a very large temperature gradient. So even though my stainless steel chamber is at room temperature, there's literally, not literally, but there's very little coupling between that stainless steel chamber and between the atoms, because the atoms, as I mentioned before, are very well separated from the stainless steel chamber, and there's just a vacuum. And the only thing that's connecting them is this laser beam. And this laser beam doesn't really couple well. There's no thermal coupling. So it allows me to thermally isolate these systems pretty well. Of course, there'll be sort of intensity modulation, say in my laser beam, or if my laser beam direction is changing, that'll heat up the atoms. But they're very well isolated for all intents and purposes.
For now, okay.
Did you have another question, Hong Tao?
Yeah, so I maybe I misunderstood this, but you mentioned the BEC versus the fermions, and I thought you've been using group 1 elements. They all have the similar 1s structure. They all having this 1 electron from the s orbital. Why are we talking about the Fermi-Einstein condensate versus the fermion? Where does the BEC come from?
Right. So I sort of glossed over this fact. But when I'm calling these bosons and fermions, certainly, the electrons that are in these atoms, this valence electron is fermion. But when I'm thinking about the atom, I'm thinking about them as a composite spin. That is to say that I'm considering both not only the spin of the electron, but also the spin of the nucleus. And that will depend upon nuclear physics, which depends upon, the number of protons and neutrons inside. So it turns out that for example, here is the energy diagram of potassium on the left-hand side and and lithium on the right-hand side. That depending upon the isotope of atom that I choose, the nucleus will have different spin statistics. So when coupled with spin electron, think about the entire system as one giant composite spin. I can think about them as being a composite boson or a composite fermion. So for example, you can see for lithium-7, one of its states has a total spin of 2, which is an integer, right? But then for say potassium-40, this ground state will have a half integer spin. So from a composite standpoint, where I'm accounting for both the nucleus and the electron, it will be a composite fermion or composite boson. That's how I can create both BEC and a degenerate Fermi gas, of course, with different isotopes. These are, I only consider one isotope at a time.
Okay, great. Yeah, thank you.
So we have another question in the chat. So Kevin is just wondering about sort of the lab particulars and is wondering like how heavy the machinery in your lab is. And what's the heaviest machine that you have in your lab or piece of equipment?
So heavy, like in the literal sense, like weight?
I think so.
Okay. Yeah. So so it's, in fact, what's sort of funny about experiments is that they're sort of one giant apparatus. It's hard to tell scale from these photos, but the entire experiment, at least this at UCSB, is just this table and this table. So there are just 2 optical tables. And in terms of heaviness, to have your laser not be sensitive to vibrations, or coupled to the fact that you're like walking around, these optical tables are really heavy. I don't actually know how many pounds they are. Wow, I actually don't know, but the optical tables, themselves are the heaviest object. And then the stainless steel chamber that sits upon them is also heavy, but maybe only about 100 pounds or something.
Cool. So we're just about at 5 o'clock. Are there any final questions? All right. If not, let's thank Dr. Fujiwara one more time. Thank you so much for the excellent talk. So next week we will have Jacqueline Benitez, who works at the Academy of Science in San Francisco. She'll be talking a little bit about science education. So I hope to see you all there. And thank you again, Dr. Fujiwara.
Thank you.